Okay, so we are recording also the lecture. Okay, the two types of problems I would like to solve today will be a problem like this, for which you have seen before, and I will, in fact, solve the problem for you, but we're going to make it a little more complex here. And you have the solution for this will be included. I will solve for you one that has one more complexity. And then we are going to solve it like here. This is the solution for this problem that I'm not going to repeat. Excuse me, this is the solution for this problem, which I'm not going to repeat, but we are going to solve it a little more. I will complicate it a little more and then solve practically a new problem. And then we'll solve it with equations, and then we'll solve it with a Smith chart. So this is going to be problem one. And then what I would like to do is to solve this problem for you. Okay, so we'll remember a little bit things from magnetostatics. All right, so let's go to this problem. And what I will do here for you is, so first of all, I will add a new page here. And what this problem really says is to find the lengths of the lines. All right, so practically what we have one transmission line here, which is connected to a resistor R. So here insert nothing. So we'll put a resistor at the end of this. And then this is connected to a series stub. Like this. And this one here is like that. And at the end, this one has a resistor. This one has a capacitor. Or in fact, yeah, why not? All right. And C. And this is R. And now what we try to do here, and let me assume that this is Z naught, and Z naught. So all of them have the same characteristic impedance. And then here you have a source, and this is 50 ohms. Z naught is 50 ohms. And this one is Vs, and assume that Vs is 1 volt. All right, all of them are in phasor form. That's why you don't see time in here, obviously. And I would like to find now this distance, D, and this distance, D sub S, okay, so the reflection coefficient right here is 0. So if we assume that this is, let's put points here. That's what you're gonna always do. So here is A prime, B prime, C C prime, okay, and D prime. So what I want here is practically, I would like to do this and move it up and also make it smaller, all right, to be able to solve the problem then. Okay. This is the problem that, that we need to solve here. And we're going to solve it with equations first and then with a Smith chart. Let's assume what I need to give you additionally to be able to solve the problem is the resistor here. So let me give you these 50 ohms. And I need to give you the capacitor here. And let's assume that this is 5 femtofarads. And let's assume now that omega, since I gave you the frequency, omega, which is 2 pi f, I give you f to be 10 gigahertz. Okay, so that's what I have here. And I would like to find D and D sub s. So gamma here at BB prime. So we need to have gamma at BB prime equal to 0, which means that we need to find D and D sub s. All right? Now let's see. We need to move, as you can see from here, we need to find a distance D. So when the resistor moves along this line towards the generator, when we move like this, then we need to have here an impedance, which I will call Z in at BB prime, so that these combine in parallel with the other impedance that I see inside the stub at BB prime, which I will call Z sub s at BB prime. We need these two in parallel configuration to give me 0. Okay, so practically, if I were to simplify this, I would say what I need is the front part of the line at, to see two impedances at BB prime, one coming from the stub, which has a capacitance at the end, and the other coming from the resistor, all right, where this is Z sub s BB prime. So let me erase that to make it Z sub s. So this is Z sub s BB prime. And this is Z in BB prime. So we need to find those. So this one here is 0. But since they are parallel, what did we say we do? We turn all of the input impedances into admittances. So practically what we do is that we would like this one, instead of impedance, to find an admittance here. And for this one, instead of an impedance, to find an admittance here. And also what we would like is to normalize everything. All right, so we would like to normalize this and to normalize this because the characteristic impedances are the same. So practically what we would like here is, instead of those, to have two parallel admittances normalized and another one, which is Y in BB prime. All right, and when we have these two normalized, the combination of the two is a sum. So this combination is going to give us a Y load at BB prime, which is going to be YS, all of those normalized at BB prime, plus Y in at BB prime. Okay? And we would like this to be equal to what? For this reflection to be 0, we would like this to be equal to 1. So practically, we would like this sum to be equal to 1. Okay, now, instead of having a capacitance, and at the end, and of course you have the 50 ohm, but instead of having a capacitance, the load at DD prime here, which you need to remember to convert into this capacitance into a load. You can do admittance or impedance load, and since we are going to be working with admittances, I will do an admittance load. So what that means is that I will, from here, rewrite that the Y at D prime is J omega C. And the normalized is going to look like that. Why did I put this line? Okay, and then make that smaller. Here. So, and then of course, this from here, we get that the Y at CC prime is going to be 1 over R Y naught. Where is, what is Y naught? Where Y naught is 1 over Z naught. Okay? So all of this is preparation for the solution. But if we prepare the solution well, then it's going to be very easy for us to find it. So then, what do we have? Again, let me write here. We have that Y CC prime normalized is 1 because R is 50 ohms, Z naught is 50 ohms, so that is 1. And then we have that Y at D prime equals J omega C over Y naught. And then you have to calculate, which is going to be 2 pi F and C, and Y naught is 1 over Z naught. So practically it's going to be 2 pi F, which is 10 gigahertz. So together it's going to be 10 to the 10 hertz. Then C is 5 femtofarads. So it's 5 times 10 to minus 15. And so that's that. And then times 50. Okay, so let's see how much this is going to give us. It's going to give us 2 pi times 5, which is 10 pi. So 10 pi here. 10 pi. And then we have 1/10 from here and another. So we have this, and this gives us 10 to minus 5, and another, so we have 10 to minus 5 times 50, which gives 5 pi, 1/10 from here and another from there. It gives us time 10 to minus 3. Okay, and that is 1 over ohm. So practically this one, so if we have 5 pi to be approximately, so here 5 times pi gives us about 15.7. We have that y at d prime equals to 15.7, 10 to minus 3, 1 over ohm, which makes it, well, 0. Let's move that a little further out here. And this one makes it 15.7, 10 to minus 3 is equal, can I write? Is 0.0157, 1 over ohm. All right, so these are the two values we found. One here at the end, the other at the other end. So, two equations that we have to solve from this one. Any questions so far? Thank you, Cameron, for giving me the values. But do you guys have any questions so far before I proceed for the solution? What about the J? Yes, the J is important to be there. And I need to add it here and here and here, 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 and there. Thank you. So now we need to insert another slide and continue there. All right. So what we have to do to make sure is, and then that we get that we find a y input at BB prime, which in fact, according to what we have found, is going to be y at CC prime plus J tangent beta D over 1 plus J y CC prime and tangent beta D. And then we have that ys at BB prime, normalized all of this, will be y at BB prime, DD prime. What did I have here? DD prime plus J tangent beta D S 1 plus J I D prime tangent beta ds. And we need the sum of the two to be equal to 1. But before we do the summation, we have to simplify some things again, because if we put everything the way it is right now in the summation, it's going to get very long equations, and it's easy to make mistakes. So from the first one, so 1 here gives us that y input BB prime equals 1 plus J tangent BD over 1 plus J tangent BD, which is something that we should have stated from the beginning, because what happens here, when R, that I will show it to you here, when R is equal to 50 ohms, then the reflection coefficient at any point on this line is what? The reflection coefficient on any point of this line is 0. And therefore, when the reflection coefficient at any point of a line is 0, here along this line, then the line is matched, regardless of what length it has. And that's what we found. So from here, we come here and we find that the input impedance, which is right here, you see the input impedance at BB prime, the input impedance here, and the input admittance there, normalized, are 1, which means that as we look at this line towards the resistor, we see always a matched line. We don't see any reflections, in other words. So we found that here. Now let's look at the YS BB prime. YDD is a reactive load, and we found practically that is 0.0157. So is 0.0157 plus J tangent beta D. And then here is 1J there. And in fact, here, 1J from here, and another J makes it -1. Or in fact, I can show it to you explicitly. So I write here J 0.0157 times J tangent beta ds. And that gives us J tangent beta ds plus 0.0157 divided by 1 minus tangent beta ds times 0.0157. And now I need to move this. There. So what we see from here is that from, sorry. All right, let me, I missed it. So this one is J, tangent beta. Okay, so what we see from 3 and 4 is that 3 is 1. So we have, and then if we call this 5, then from 3, 4, and 5, what do we find? That we find that 1 plus YS BB prime is 1, which means from here that we want YS BB prime to be 0. So we want J tangent beta ds plus 0.0157 divided by 1 minus tangent beta ds times 0.0157 to be 0. And the only solution for this is the tangent beta ds equals minus 0.0157. And then from there, you can find the value for ds. All right, so, and the value for ds, if you have a calculator, and you can give it to me. So that is how we would get this solution by using equations. Before we go and try to solve the same thing on the Smith chart, do you have any questions? So practically what we found is that we can select any D for the straight line. We can select any D here. And for there, the ds that we will select, it has to be given by this equation down here. By this one. Has anybody been able to find the value of ds in lambda for this one? When you find it, it's 0.0025. Is either that, or let's assume that we get this solution. Somebody told me that this is, and it should not be 0.0025 because that would give us a positive. It has to be negative. So what is it has to be a negative value. So you cannot be negative though, all right, for the length. So what is it? That we have to extend the length. We have to extend the length until the YSBB prime becomes 0. So meaning the tangent of BDS becomes 0. So where does the tangent of BDS become 0 or close to 0? All right, but it has to, for it to be negative, we cannot get a negative length. So in fact, what if I were to do this in plus 2 pi? That may, yes, or what could it be? If it's negative, it can be negative or plus 180, not 2 pi, plus pi. Because if the tangent is negative, here, so here it's an angle. For the tangent to be negative, you can be down here. All right, so your cosine is positive, your sine is negative, or it can be up here. Your cosine is negative, your sine is positive. So it's either this one or this one. All right, so it's plus pi, not plus 2 pi. In the BDS, it's plus pi. So let me, in fact, do it for you. So to see, insert another. Okay. So what we have in this one, if you follow me, you have tangent of beta ds is minus 0.0157. And if you know the tangent BDS, if this is my angle, and this is, okay, so if for this negative and very close to 0, obviously, this phi here can have tangent of phi to be negative, minus 0.0157. But since we cannot have a negative argument, so we go here, which has the same tangent. So from here to there. So this phi prime is pi minus phi. So what we do is we find the arctangent, tangent, calculator, because I don't have it on my, let me see, arctangent. Oh. All right, so it's 0, point negative 0.0157. That gives us, in degrees, phi would be minus 0.8994 degrees, or will be approximately 179.1 degrees, okay, approximately, which in fact tells us that beta ds has to be 2 pi ds over lambda. 2 pi is 360. So, and if this is phi, it means that ds over lambda approximately is going to be what? It's going to be 179 divided by 360, which is 0.49. That's your ds, okay? And that is the solution for the problem, because then when you do that, you find that finally your y total at b prime normalized will be 1. So if we go back to this one, then you find that the total y here, all right, is going to be 1. So we got that, and therefore the reflection is going to be 0. Now, let's try to see how we would solve this on the Smith chart. So on the Smith chart, we said we are going to work with admittances, all of them. And we're going to find y Isabel at bb prime, and we want this normalized to be 1. Okay? Now, let's assume we don't know anything about the analysis we did for this problem, but we know that we have to work with admittances, this one, and this one, and we have to find these admittances on the Smith chart. So practically, one admittance, the y input at bb prime, we know this normalized is 1. So practically this admittance is going to be here already, but it's only this admittance, and then we have the stub. It's not, we're not done, because if we keep this the way it is and then we just put the stub anywhere, it's going to move this point off. So then we have the other y s at bb prime, which is minus j 0.0157. So now, since this one, and we have that yl of bb prime is 1 plus y in at ys at bb prime. ys at bb prime. Okay, so we want to stay at this point. This is my y in at bb prime. Where is ys at bb prime? And if it's minus j 0.0157, I have to go to the lower end of the Smith chart, and practically it's gonna get me down. This is the x-axis, if you remember. At this point, all of the admittances are 0. And so we have to find an admittance here, which is somewhere here. Okay? And we will need to make sure that we move this until we go into 0 practically, but we cannot move for this small distance because it's too tiny. It's like you bring the capacitor, maybe, you know, you can bring the capacitor and put it, but the stub is so short that you cannot even make it. So practically, I need to go to the next length of the stub that will be more to make and easier to fabricate. So what I do in this particular case is I want to come back to this point on the Smith chart, right somewhere here, because that gives me 0. So I move around the green point. Let me see. And I move towards the direction of the generator. So like this. And I will move around by half a distance until I come here and I move to this point. So practically, I move by half a wavelength to be able to get there. So it gave me either 0, because I gave you a very small value of the capacitance. If I had given you a different value of the capacitance, then you could have seen that it would have been a totally different situation because we would not be that close to 0. But in any case, we move until for half a wavelength and a little bit tiny, you know, over half a wavelength to be able to find that point. So that's where we are. This is the solution of this problem on the Smith chart. As you can see, I could have come with this without doing any calculations. These are the only calculations I would do on the Smith chart, as opposed to what I did here. I did those, and then I did those, all right? And then I did those. So I don't need to do all of these calculations if I am on the Smith chart, because practically, you know that if you have a transmission line, and the transmission line has a section, it has a length D, and then at the end, you have a resistor which is 50 ohms. So your load is 50 ohms. You know that this is always matched. So at any point on this line, this input impedance here, normalized is going to be 1. Or admittance, if you want to use admittances, normalized is going to be 1. So that always comes out to be the case, and you don't even have to have any calculations like I did before to see that it also comes out in the form of calculations. And then from there, you find out that you are here already just from your load. So whatever capacitance you want to add, you don't want to admittance you add there. You don't want this admittance normalized with respect to the admittance to be anything that will change the value of this point. So practically, you want to make sure that your admittance, when it comes there, is 0. All right. So the total admittance, when the admittance is close to practically 0 there when it comes there, if not exactly 0. And that it gives you the value that you need to have at that point, the length. And from that, you find the length of the stub and the length of the line. Do you have any questions here? Any questions for this problem? So when I when I give you a problem for the final, now I took a long time to explain it, but this problem you could have solved in half an hour. All right, when I give you a problem like this, then I said I will also give you a Smith chart, but I will ask you to use one or another. For those of you who feel comfortable using the Smith chart to get the solution faster, you will be able to do it. It does not mean, however, that I will ask you to use the Smith chart. I will just leave it there in case you want to use the Smith chart, or if you don't feel comfortable, you want to use equations, then you use the equations. Now, I have office hours today. So for those of you who have problems with Smith chart transmission lines, since you know that this is going to be half of the meter, I would like you to come to the office hours, tell me any questions you may have. I also will have office hours tomorrow. So tomorrow we have a class in the morning because it's a makeup day for Friday, Good Friday. And so we are gonna solve problems again. Yes, we'll have a top hat today, and the top hat is gonna start at 12, from 12 to 6. And tomorrow we'll also meet at 8 in the morning. I will solve you this other problem with the currents that you saw before. And then also tomorrow, tonight, as I said, I will have the rest of the solutions for the makeup assignments. And I will make those available to you. And I will post it. So you will have the makeup assignment and solutions posted for you to practice. Any questions that you may have for me? Any questions?
Professor, in regards to you mentioned that there's going to be a couple questions from the first part of the semester.
Yes.
Is there anything in particular that we should focus on? Because, you know, for the second part, you're telling us to focus on Smith charts and stuff like that.
Yeah, like problems like this, not exactly that. I will solve this tomorrow. A problem like this, let me show you some other problems. A problem like this, which you will see the solution. All right, we've done those. This is for capacitance to calculate. I may have a dielectric in there, like in the meter, or a problem like this, where you have charges, and then I ask you for the flux, you know, through a surface to see how many charges are included inside the surface. That or these, not all of them, or these or some type of this, but not maybe with a square. It could be another, a circle instead of the square. This is what I was thinking. All right, these are the types of problems we have solved so far. And then from transmission lines you have seen, which is the last part of the class. One problem in the individual is going to be from the first part of the class, what I showed you, like calculation of a capacitance, something like this that I have in front of you. And the other part is going to be from the second part of the class, like a load with a stub, maybe something like that. Let me see. This one is an induced inductance problem. Yes, so it's an induced, it's an EMF induced. It's not an induced inductance, it's an induced EMF. One where practically when your flux through an area changes, that you have an induced voltage there. Remember that? Yes. Yes, I will post the makeup solution, the makeup, you mean, yes, the makeup solutions, makeup assignment solutions later this evening. I will do that. You have 2 hours to take the exam, and then I will give you another 15 minutes to upload the solutions. It's not gonna be within the 2 hours. I'll give you an extra 15 minutes to do that. These are questions that I get, and I'm responding. Yes, go ahead.
Also, Professor, will you pretty much be releasing them kind of like how you were in the midterm, how you're going to release the individual probably at the beginning of class, and then towards like roughly 11:30 where you'll be releasing the
know
team?
what I will do? I'll tell you what I'm going to do. I'm going to give you more flexibility here. I'm going to give you both. I'm not going to release one right after the other. I will give you both the individual and the team. You're going to see the problems in front of you. And for those of you who have been very fast in the individual, they can start the team. For those of you who need more time with the individual and they can do the team later, it's your decision on how to do this. So talk with your teams and be ready. I will just give to you. If you are done faster with the individual solution, I don't want you to stick around if you think you can use the time for the team. So I will release both of them. They will be the same types of problems, but 2 questions for the individual and then 2 additional questions on the same type of problem for the team. I will release them at the same time. You manage your time, how you want to do that. Ideally, I would like you practically to do 1 hour and 1 hour, but in a final, in a final, we give you all the problems up front, and we normally ask you to manage your time. So remember that the expectation is I'm going to design the individual and the final. So one needs 1 hour, the other needs another hour. So practically, that's what I have in mind. But again, for those of you who can finish one fast and then your team can start the other one, or you can start looking at your team problem before anybody else, you're free to do that. But I expect you to upload your own individual exam individually, and your team, I expect upload one file for the whole team.
Okay, just 2 more questions. One, will we be sent a separate Zoom meeting for the final time? Because I believe our final time is Thursday at 10:30.
12, yes. You can do Zoom meeting because I will be there. I don't want to, I'm not going to be like the other faculty. I don't want to watch over you. Don't need that. You're adults. We all are adults, and you are responsible for it's open everything, all right? What can I say? As long as you don't have somebody next to you solving the problem for you, which I trust you won't. You cannot find anybody to solve the problem for you anyways, unless your mom is an engineer or your dad. But in any case, I would suggest that we stay on Zoom for no other reason, but if you have any questions. And I will be there if you have any questions to ask me. If there are clarification questions for the problem, ask them the way you do now so everybody can hear the clarification. If you want individual questions, you can email me. You can send me a text and say, I will email you a question for me individually. And I can respond to your question individually by email.
Okay, and then my second question is, how are the teams gonna be able to talk to each other without making it a mess? Are we gonna do like breakout rooms, or how are we gonna do this?
Okay, what will be the best way for me? Do you want me to make breakup rooms for each one of you? How should we do this, you think? You suggest?
And
I can,
also, oh, I was gonna also ask if we do it that way, could we maybe towards like the latter part of next class, if we could do like a test run so we can get used to that?
yes, true. Uh, you know what is the other thing you can do? Each one of you can do a Zoom, isn't it? Can you guys do a Zoom through the university?
Yeah, students create their own Zoom meeting.
Okay, perfect. What I suggest is that you can be on 2 different Zooms, or I don't have to be on a Zoom. I can be available. I can release the exam as I did for the makeup assignment. I can release the exam through eCampus for you on the right time, both of them. And then you can do Zoom meetings among yourselves. Really, I mean, the only reason I want to be here is to ask questions. The other thing is that, as I said, Ashley said that one other possibility is for all of us to be on a Zoom, but you can mute yourselves. And then you can be on another Zoom with your friends. Or you can leave the Zoom. You know, you don't have to be on a Zoom meeting to submit the final solution. I can be on a Zoom like I do with office hours. Or I can be on a Zoom like this, and then you have to be there or not. I mean, after you take the exam, after you would download the exam, you ask whatever clarification questions you may have. You can get off my Zoom meeting. I will be there. You can get on again if you have another question. And then you can do your own Zoom meetings with your team. How about that? Does this make sense? No, I did not hear. We'll discuss it next time. Okay, well, thank you. And we'll talk to you tomorrow.